Okay, good morning, ladies and gentlemen. Welcome to the third installment on functional groups. We're talking about ketones today. So, if you remember, in the last lesson we talked about aldehydes, and prior to that we talked about alcohols. Today we talk about ketones, which is like the sister group to aldehydes. Why do I say it's the sister group? Because it kind of looks like aldehydes, just that the only difference is that instead of having a hydrogen at the end, you just have a C double bond O group which is attached to a carbon. It could be attached to both carbons on both sides. Well, mostly it is both carbons on both sides, but it's just a C double bond O group, uh, which characterizes a ketone. So how do I name it? Aldehydes were named with Al. Ketones have the suffix O, N, E. Just end the parent name with O, N, E. And what's the numbering rule? Unlike aldehydes, ketones don't have to be given priority or given position number one. Numbering rule is same as any other substituent. Same as any other substituent. Okay, so I'm going to discuss a few ketones. The first one that we're going to discuss is propanol. So for propanol, you have three carbons, and the C double bond O group is right in the center. You have a CH3 and you have a sorry, this has to be a structural formula. I always forget, not a condensed formula. So this is called propanol. Condensed structure formula would be just get rid of the bond, CH3, C double bond O, CH3. Next one is butanol. 1, 2, 3, 4, C double bond O. It really doesn't matter if you put the C double bond O, if this is position 1, on position 2 or position 3, because if the C double bond O is on this position, then you'll start your numbering from the left. If your C double bond O is on this position, then you start your numbering from the right. So in both cases you will get the name butanol. So there are no variations to it. That's why you can call it 2-butanol or butan, or just butanol, because there's only one butanol that's possible. If you condense the structure, you end up with CH3, CH2, C double bond O, CH3. Next one is pentene 2-one. Now this is where you start differentiating based on the numbering. So because pentanone can exist as 2-pentanone or 3-pentanone, that's why you would need to include the numbers. So 5 carbons, 1, 2, 3, 4, 5. Now the C double bond O group could be here or it could be here. So that's why we need to start numbering. CH, H. So CH3, CH2, CH2, C double bond O, CH3. Oh no. Okay, sorry for the pause. It was again the spinning beach ball of death. So pentane 3 on board. Look, Like, let's put the double bond O group here. Doesn't really matter. I just don't have enough space. So I'm going to put the double bond O group at the bottom. That gives me CH3, CH2, C double bond O, CH2, CH3. That is pentan 3 on. I'll give you a minute to take this down. Okay, so now that you have the structural and the condensed structural formulas and a few examples of the common ketones, let's go on to a question. Now we know that propanon, the first ketone that we drew, we drew a structure of the first ketone here, which is propanon. Propanon is infinitely soluble in water, while hexanon is slightly soluble in water. I want you to spend the next 2 minutes thinking about why that is, and then offering a valid explanation. Explain. Thanks. Okay, so the reason behind this is that propanon is a small molecule, and in the small molecules, the dipole forces. So in smaller molecules, dipole forces overpower the dispersion forces. As a result, propanon would hydrogen bond with water. Now, if you're wondering how did that happen, well, it can still hydrogen bond with water. It can't hydrogen bond with another propanon molecule. For hydrogen bond to occur, you can just have one molecule which has hydrogen bonding in it, and propanon, because it has a dipole, it will still be able to have that intermolecular force working for it. So the oxygen, the highly electronegative oxygen in the propanon molecule would be the lone pairs of electrons on it would be attracted to the hydrogen in the water molecule. Let's illustrate this with the diagram. 1, 2, 3, 4, 5, 6. Let's just draw it somewhere else. So think of it in this way. So you have C double bond O, 1, 2, 3, 4. C carbon here, CH3. The carbon here, CH3. And you have a water molecule in the vicinity. Now, for a hydrogen bond to form, you should have a molecule in which hydrogen bonding occurs. So if you look at this oxygen molecule, the oxygen atom, it is bonded to the hydrogen atom. So the criteria for hydrogen bonding is fulfilled in a water molecule. Now, what will happen is you have a lone pair of electron here. This lone pair of electron would be attracted to the hydrogen, and that would result in a hydrogen bonding. So hydrogen bonding does occur even though there's just one propanon molecule and one hydrogen molecule here. But in larger molecules, what happens is that the dipole forces in larger molecules, the dipole forces, that's called dp forces, are much weaker than dispersion, and as a result, larger molecules are more soluble. Are soluble in non-polar solvents. Not water. Simply because of the dispersion forces which are stronger in larger molecules. Okay, I'll give you a minute to take this. Now that we have covered ketones, let's move on to another functional group, and this is a really famous one. It's called carboxylic acids, and a carboxylic acid group would look something like this: COOH. So you remember the ketone group which had a C double bond O? Now we are just replacing one of those bonds with an OH. How do we name it? Just an ACI, an IC, and we end the name with an acid. Numbering position. Oops. Thank you. Oic acid. Yep. The numbering position is similar to aldehydes. You really don't have to give it a number. It's always at the end. So, numbering position is 1. So, no need to put a number in the name. Yeah. Yeah. Name. Let's just go through the few acids. First one's methanoic acid. This is the acid that is found in red ant bites. So HCOOH. Oops. Structural formula, as always, I forget that. HC double bond OOH. Condensed structural formula is HCOOH. Oh wait, I have to give you my second. I'll pause this for a bit. Okay, the next one is ethanoic acid, which is like really weak, just like Adi. You took a day to come up with that, right? You spent the whole day. I used that one on you already.
That makes sense to me.
Okay, so this one, the condensed structural formula would be CH3COOH.
That's recording, isn't it?
Yeah, that has recorded.
It's gonna go viral now.
Sure. So propanoic acid would look like C double bond OOH. Now you need to get really familiar with doing these things, drawing the formulas, structural formulas, condensed structural formulas, because when we get to the next topic, which is doing reactions, in which we'll be doing reactions for alcohols and esters and carboxylic acids and ketones and aldehydes, you just need to know. You'd be just given the name of the aldehyde and you'd be expected to draw it. So you should be really quick with it. Butanoic acid, same thing. 4, 1, 2, 3, 4. And C double bond OH. So those are all the structural and condensed structural formula for the first 4 acids. Now, I have a question here which I really would like you to think about. And the question is, why are boiling points of carboxylic acids higher than the parent chain alkanes? So, as you think over it, I'll give you some time to think over it. And we'll continue this in the next video. Thanks.